All right, last video for us. A little bit more practice with these and you guys will be good to go. You'll have models for solving other problems. All right, so it says, what is the equivalent resistance to the circuit below if I wanted to use just one resistor? Now, this is a bit of a mess because there's two places where we have parallel going on, and then there's a couple different places where we're going to have series going on. So basically, when you work on one of these problems, what you need to do is think about it inside out. So I'm going to handle these guys first. And then once I've got them worked down into a single piece, I'm going to switch and handle this. But remember, those green guys will be down to one single resistor. So I'll be going from handling a parallel to a series. And then I'm going to work out one more time and handle this parallel set. So you can see how when I draw boxes around them, it's working from the inside out. All right, so let's tackle this bugger. The first one is a parallel set. So I need to go back and look at what do I do with resistors when they're in parallel. We just took these notes. So I'm going to do 1 over 90 plus 1 over 45, and I get 0.033, but I know that I need to reciprocate that, and it works out to 30 ohms, very neatly, like some textbook came up with this idea. All right, so that means that I can take out the 90 and the 45, and I can put 30 ohms in here. All right, so the next piece is the 10 and the 30 in series. So if we go back into our series notes, this is an easy one. I'm just going to add them up. So now I can take out the 10 and the 30 and I can just have one 40 ohm resistor over here. I've wiped out that whole side. And then the third one, the last one, I've got a 40 and a 60 and they're in parallel. I can go one way or the other. I can't get them both. So I'm going to do 1 over 40 plus 1 over 60, and I get 0.042, and I know I need to reciprocate that, and I'll be darned, it works out neatly again. I could put in one 24 ohm resistor in my path, and it would do exactly the same thing as all these other guys do. All right, so that's that question. Inside out, that's the notes we want to take away from this one. All right, so I need to move forward and get these last couple pages. All right, this one says find the equivalent capacitance of the combination and then find the charge. All right, so I've got some of the same problems that I had before. I'm going to set up my inside out. I've got to fix these guys, and then I can fix this one. This one's a little simpler because they're asking us for two different things. Okay, so here we go. Step 1, do the green step. This is two capacitors in parallel. So if I've got parallel capacitors, I just add them up. 5 plus 1 is 6 microfarads. Okay, that wasn't too bad. So now I'm going to put a big old 6 in there to let myself know not to pay attention to those anymore. But then I have capacitors running in series. Okay, it's all right, we can deal with it. I'm going to take 1 over 3 and add it to 1 over 6, and I get 0.5. And got to do 1 over 0.5. I get 2 microfarads. Textbook pretty. Okay, so that's the equivalent capacitance. That's my CEQ. That answers the first question. And then the second question is, find the charge. Well, charge is Q. I have a voltage. And I have a capacitance. I should be able to do this. If I go digging back in my notes, I find capacitance is charge divided by voltage. So charge is capacitance times voltage. We talked about this once earlier in the video series, so the next step for me is getting my numbers right. So Q equals 2 times 10 to the negative 6th times 12. And I get 2.4 times 10 to the negative 5th. I'm measuring charge, coulombs, not capacitance. Now, if you're an engineer, you're going to write that as 24 microcoulombs. Either one of those answers works for me. Not too bad, right? It's just a matter of having those two processes, those two little sections of short notes in front of you so that you can say, I'm looking at this. Okay, this is what I do with it. Now I'm looking at the next step. Not a big deal. Just that piece, that's what I'm going to do with it. Okay, so while you're calm, this problem takes a little bit of work. Okay, it's on its own page, but we're going to need all this page to get her done. It says find the current and potential difference across each resistor. So on each resistor, I want to have a voltage and a current. A voltage and a current. And I'm going to take this 400 and set it over here. A voltage and a current. And this guy down here needs a voltage and a current. Okay, the process isn't hard. This is time consuming. Okay, so I'm going to look at this inside out. The first thing I need to tackle, and I'll grab green because I've been doing green first, is putting these two together. So I've got resistors in parallel. Okay, so resistors in parallel. I need to do 1 over 600 plus 1 over 400. I'm going to get something. I'm kind of hanging to see if you guys will catch up. .0041666666. Leave that all in your calculator. Don't round just because you wrote it down to remind yourself. Leave it all in your calculator and do 1 over the answer. And you should get a nice rounded 240 ohms. Okay. So if I were to redraw right now, and I'll do this relatively quickly, I would have the 800 going this way. Over here I would have a single 240. And then coming down this way, I have my 560. So it's already looking a little bit simpler. Okay, so the next thing that I want to tackle are the two that are in series together. So I'm going to pick a new color here. I'm going to tackle these guys. Okay, so here we go. This is going to be fast. 240 plus 560 equals 800. So now I have 1/800. That is a terrible resistor, by the way. And I have I'll do better. Another 800. Okay. So there's nothing left to handle except those two 800s. I'm going to scroll down just a little here. And I have two 800s in parallel. So parallel means I'm going to do 1 over 800 plus 1 over 800. And I get, I'm going to reciprocate, I get 0.0025. And when I do 1 over that, I get 400 ohms. All right. So there's my single equivalent resistor. Now I needed that to do the next step here. And the next step is find the total current. So V equals IR. Now I have one source of power and I have one resistor. Whoops. So my current is 0.03. Well, that would be amps, or 30 milliamps if you're going into an engineering field. Same answer, move the decimal. Okay, now this is what's going to blow your mind, is we've got to backtrack out of this to be able to put a voltage and a current on each piece. All right, in order to stay with my picture, I'm going to erase. It's okay because you have a rewind button. So if you need to rewind, you can. Okay. So here goes. Remember, don't panic. You have a rewind button and it works. I hope. Oop, I lost my eraser. All right. Now, I am going to undo things step by step. I'm going to go back in the opposite order. So I'm going to draw a circuit here. And I'm not worried about the resistors. I'm worried about the current. So I'm going to write milliamps, if that's okay, because the numbers are nicer. So here's my milliamps, and here comes a junction. And at this junction, I know that the resistor down each leg is equal. They're going to get the same amount of resistance. So when it hits this junction, that amperage is going to split. And going this way, I'll get 15 amps. And going this way, I'll get 15 amps. Okay, well, this resistor right here, he's isolated and he doesn't recombine or uncombine in any way. So I can go over here to this 800 ohm resistor and I can label that it's going to have 15 milliamps of electricity running through it. Okay, so I put my first number on my final stuff. That feels good. All right, let's move on to the next piece. I'm going to go back and draw it in black just so we can see where we started. I have 15 milliamps coming in. And I have to run it through this resistor, which we said was 240 ohms. And turn the corner, corners are irrelevant, but turn the corner and run it through this 560 ohms. Now these guys are in series with each other. Okay, so we need to look back at the second video that we watched. And there's a little reminder there for us that says when we're in series, current is constant. So that means that this one's going to feel 15 milliamps. Oh, I just moved it. That was strange. And this one's going to feel 15 milliamps. Well, again, the 560 is one on our original picture. So now I know this one. And I have another piece of my puzzle done. All right. We'll go back and look for these voltages in just a minute. All right. I just don't want to stress anybody out. We're almost there. The last piece of the puzzle. I'm going to go back and draw a circuit one more time. Here we are back at this. And we know that going into this, we have 15 milliamps. And it's going to get split so that 60% of it goes up and 40% of it goes down. Okay, I paused for a minute for a reason. And hopefully you said, hey, hang on a second, Shannon, because what stays constant at a split isn't the current, it's the voltage. And we need to know what that voltage is to know what that split is. Voltage is constant when we're in parallel. Okay, so that means we need to back up for a minute. I know that there's a lot of steps to this. This is the hardest problem that we're going to do. That's why it's the end, but we can do this. Okay? I'm going to clear out a little workspace right there. Let's go back up and look for voltages. Okay? Anywhere that I have an R and an I can calculate a V. I have to use my units correctly. So let's do the first one where we did it in green. I have V equals IR. Okay, well, the voltage, hang on one second. V equals IR. The I was 15 milliamps, so 0.015, and the R was 800. So type that in your calculator real fast. And what you should see is a voltage drop of 12 volts. Okay, hang on, does that make sense? That's all of it. Well, remember, Kirchhoff said from the beginning to the end of any loop, it has to cancel. Well, if you go down that first 800 loop, the electricity is only going to hit that one resistor and it's going to go right back into the battery again. So everything has to be lost. Awesome. So 12 volts. But once we split, I'm going to stay in green just so that you guys can see where I'm going. Once we split and we come over here and we're looking at the series, the voltage has two places where it gets to go down. So Now that I've shown you where I'm working, I'm pulling my numbers from that second chunk of circuit. V equals IR. Well, the first circuit is 0.015 times 240. And if I do that, I should get 3.6 volts. And the second part that it's going to run into 0.015 is 560. And if I work that out, I should get 8.4 volts. Well, what happens when I add 3.6 to 8.4? There's 12 volts there. That's perfect for us because if it travels down that pathway, remember, this represents our parallel guys, and this is the one in series with them. We're talking about going down this path right here, and if we do that, we need to lose 12 volts so that when we get back to the battery, we've lost everything. So that Kirchhoff is right. Okay, well, that means that my 560 is going to lose, it's going to have a potential difference of 8.4 volts. But it also means that these guys over here in parallel, where voltage is constant, are both going to have 3.6 volts. Both of them are going to have 3.6 volts. So I can put a 3.6 volts up here, and I can put a 3.6 volts down here. Well, now I should be able to figure out what part of the 0.015 each one gets. Same equation, V equals IR, rearranged. We've used it this way several times. That's not new. All right, so I'm going to do it for the first one. And I have 3.6 divided by 600. So do that in your calculator. And you should get 0.006 amps, or 6 milliamps. And if we do it again for the second one, we have 3.6 divided by 400, and we should get 0.009 amps. So remember when I said 60-40 split, I wasn't wrong about the 60-40 split, but what I wasn't right about is that the bigger part, the 60% part, goes down to the bottom. And the smaller part, 3.6 volts, 9 milliamps. The smaller part goes up here to the top, 0.006 amps, or 6 milliamps. Now, if we think about the fact that IR has to be equal to V, if there's a bigger resistance, there has to be a smaller current. If there's a smaller resistance, like the 400, there has to be a bigger current. But you can take those numbers and backtrack, and they both will add up to 3.6. Now, if we look our way around, we've solved all of them. But if we go back to our notes, and I just want to show you this quick because this has been a long enough video, and we go all the way back to the beginning. Whoops, they're not even there. They're so far in the beginning. And I told you there was a process here. Draw a diagram using the proper symbols. We've had a lot of practice with that. Break the circuit down. That's what we did when we took the parallel, turned them into series, combine the series, and then combine the parallel again until we get down to just a single component. Find and label the pieces that you need at that point. So what we needed was current, and then rebuild the circuit backwards, keeping track of whether or not it's current that stays the same or voltage that stays the same, and do it piece by piece. Now, how can we check? Well, when we go back into this, oops, one second. When we go back into this big problem and we look, everywhere that we've written stuff down, we should be able to do V equals IR and it should check out. So all 4 of those should check. Any circuit I take, the change in voltage needs to be 12, and that checks out. And our units need to be careful. So remember, if you're going to do math and I wrote down milliamps, make sure you put in 0.015. But you should be able to check voltage dropping, following Kirchhoff's rule, which is where we started, and you should be able to check V equals IR. If you can do that all the way through, then you've done your problem right. If those pieces don't add up the way they should, something along the path went astray. Okay, not going to lie, you're going to have a problem like this on your take-home exam. You'll be able to watch what we did and hopefully go back and apply it to a similar problem. If you want to practice more, there is a link to physicsclassroom.com and they have 72 problems with worked out solutions there. So you should be able to find problems like this and practice on them. And if you need any more help, let me know during class.